Hi, I'm Craig. I'm a mechanical engineering student at Heriot-Watt University in Edinburgh, and over the summer I did an internship with the International Space Elevator Consortium. I researched and wrote a paper titled Application and Uses of Robotics for a Space Elevator, where I investigated type of robotics that are in use today in the space sector, identified type of robotics that will be needed to operate and maintain an enormous space-based megastructure such as a space elevator, and offer potential conceptual design for these future robots to be implemented. Space is an incredibly harsh and dangerous environment for any life form to survive in, especially humans. The dangers of space to human astronauts are already well known and include a decrease in bone density, loss of muscle, and even weakened immune system, and increased lifelong risk of contracting cancer. All of these mean that if possible we should use robotics in place of astronauts as much as we possibly can. As many of you will know by now, building and maintaining such a large structure as a space elevator is no small task. Although the benefits of being able to build one are clear, it's still a large challenge to undertake. My paper was able to identify 5 areas where robotics will be able to help in the construction and maintenance of a space elevator. These include the construction phase, when the tether is initially built, and for the continuing maintenance and repair of the tether should any of the parts be damaged. A cargo manoeuvring system capable of safely and precisely repositioning incoming cargo to a safe location. Debris tracking to track the numerous and exponentially increasing amount of space debris in orbit around the Earth, any one of which could cause severe damage to a tether. Debris removal to be able to safely intercept and remove or reposition any debris that have been identified as being on a collision course with the tether. And finally, an orbital cargo tug, which will be able to deliver incoming payload to client desired target orbit. Robotics are already used in a wide range of activities in space today, including the carried arm on the Space Shuttle and International Space Station, which can maneuver cargo. NASA's Robonaut concept, which were designed to help on International Space Station, are also being able to use any tool that the astronauts could also use, and also SpaceX Dragon spacecraft and the European Space Agency's automated transfer vehicle, which can both autonomously dock with the International Space Station. The benefits of using robotics over any astronauts are clear. They're easier to maintain, consume less resources and power, and generally have a significantly longer lifespan than any period of time an astronaut can safely operate in space continuously. A dedicated construction climber would be able to continuously climb up and down the 100,000 kilometer long tether safely, replace or repair a damaged part of the tether with no risk to any of the astronauts. My concept for the implementation of this construction robot would be to launch an initial very lightweight tether, capable of only supporting the weight of a small, specialized, lightweight climber. This would have to be achieved by conventional means using a rocket to deliver the initial payload, meaning mass optimization would be important. This can be achieved by using composite material, such as carbon fiber, for the climber. After this initial lightweight version of the tether is in place though, the construction climber would be able to continuously climb up and down with more and more strands, continuously increasing the strength of the tether until it is able to carry normal loads. To power the climber, rigid fixed solar panel can provide enough power for the climber to slowly make progress as it ascends through the thick atmosphere. Once at a sufficient height when it clears the atmosphere, however, it would then be able to unfold larger and more fragile solar panels, which would then be able to give it enough power to climb more rapidly to the other end. Once payloads have been delivered to space, they will need to be carefully relocated to a safe spot to allow incoming payloads to also be delivered safely. This cargo maneuvering system could be implemented as a robotic arm, similar to the carrier arm which can be found on both space station and the space shuttles. This would be safer than anything based on reaction control systems, as tiny errors in the firing of these RCS engines could cause serious damage to any nearby infrastructure and other payloads. For something as large as a space elevator, however, my paper suggests that this arm would need to be significantly larger than anything deployed in space previously, perhaps up to 50 meters long. However, as it is based in space, it does not need to support its own weight or the weight of its target in a gravitational field, meaning it can be made much lighter and stronger than anything ground-based. This conceptual arm would require a large amount of energy, but as the space elevator will be in almost permanent sunshine, solar panel will be able to provide sufficient power. As mentioned in other publications by the International Space Elevator Consortium, there is already an enormous cloud of debris covering the Earth, and the problem is only growing exponentially worse. A network of intelligent debris observation satellites would be able to observe all the debris and identify which one would be most likely to hit the tether. Due to atmospheric scattering, not many wavelengths of light in the lower end of the electromagnetic spectrum will be able to reach any ground-based facilities, which limits the lower trackable size to 10 centimeters, while studies show the majority of space debris is significantly smaller than this. Ground-based facilities are also only able to see a limited section of the sky at a time. A network of observation satellites will be capable of viewing debris surrounding the entire Earth at all times. According to research, in order to be able to detect objects down to a submillimeter size, radar system utilizing terahertz section of the electromagnetic spectrum would be required. These frequencies are also very strongly absorbed by the atmosphere, but a space-based system will be able to avoid this. Of course, being able to detect debris alone is of no use if we don't have a way to safely and effectively remove it, so that it does not pose any harm to a tether. Space debris is incredibly dangerous and will continue to exponentially grow. To give an example, in 2007 the Chinese military tested an anti-satellite weapon on a Chinese weather satellite. This single strike alone generated 3,000 pieces of trackable debris as of publication of my paper. There are two approaches to debris avoidance: either track and intercept debris, or manipulate tether to avoid it entirely. A fully constructed space elevator would be able to continuously deliver as the supply of debris intercepting satellites. These satellites would be able to receive data from the observation robots and target and rendezvous with dangerous debris, and deorbit them. This could be done either with a conventional chemical propelled engine, or by utilizing electrodynamic propulsion. This is a method of using the Earth's magnetic field to produce propulsion, but this is only effective in low Earth orbit where the magnetic field is strongest. As mentioned before, alternatively, a dedicated climber could move up and down tether and physically manipulate it so that a tether is safely moved out of the way. This would be a slow process, however, and would only be used for pieces of debris that debris interceptors are unable to reach in time. While a space elevator is able to deliver payloads to orbit, they will tend to remain in the same orbit unless they are actively propelled with more conventional rocket technology. Adding propulsive elements to satellites tend to be expensive and require specialist knowledge to be able to integrate it, not to mention also taking up additional valuable mass that could instead be used on the satellite itself. A robotic satellite based on technology from the SpaceX Dragon spacecraft or Energy Progress spacecraft capability of autonomously docking with the space station would be able to latch on to or dock the payload delivered to the space elevator and propel it to its final target orbit. This could be another source of revenue for a space elevator, as these cargo tugs can be refueled with fuel delivered by a space elevator, while also offering client a valuable service. As they be permanently in space, you can use either electric propulsion or high efficiency vacuum optimized chemical rocket engines. When most people hear autonomous artificial intelligence, naturally they may tend to think of scary science fiction stories about robots taking over the world. While this is unlikely to happen, it is important to consider the advantages and disadvantages of both approaches. We are already seeing increasing automation in many parts of our life, such as self-driving cars. Any initial automation is likely to be limited to being able to execute a set of pre-programmed instructions, eventually building up a neural network capable of intelligently solving problems as they come up. This would be especially useful for when these robotic fleets potentially grow to number in the thousands. It would be extremely difficult to continue to coordinate them all manually. Of course, there are still concerns to be had about them getting out of control, so it would be important to build in a kill switch system to allow us to safely shut them down if needed. This has been a very brief overlook of the potential uses of robotics in the context of a space elevator, but it is already apparent that robotics already plays an increasingly larger role in all of our daily lives, and it is natural to assume that this will extend to space elevators. If you have any questions about my paper or research, I'm happy to answer them. I'm available at this email address. Thank you all for listening.